you recall, Professor Bernstein is out of town today, and we're very pleased to have Professor Karl van Bibber here. Professor van Bibber was educated at MIT in nuclear physics and spent 25 years or so at Lawrence Livermore National Lab in a variety of capacities, and then was provost of the Naval Postgraduate School in Monterey, and then lured him away to become chair of nuclear engineering here several years ago. And he taught the course last year. So Karl's going to give his first exposition of some basic fundamentals on nuclear energy. And then I'll follow up with some material on the chronology of how we began to move toward nuclear weapons. Okay. Thank you.
Okay. So as Professor Knox said, he is in Washington, actually taking part in a, I don't quite know why it's still ongoing, but it's actually a federally convened workshop on nuclear data. So I want to give some general remarks here on energy, to try to get everyone onto the same playing field here. I think there's the nuclear engineers here. You can step up for a latte if you wish, or you can hang around. These are some slides that I developed, and Lee has dramatically improved since last year. So here is as Lee puts it, the wild and wacky world we're getting into here. All the source of energy in nuclear power and in nuclear weapons comes from the properties of atomic nuclei and nuclear matter, something about which I have very little innate intuition or comprehension, simply because the world of ordinary matter, the chemistry of the world, binding energies associated with chemical reactions, including neurometabolism of the mind, internal combustion engines, and so forth, all has to do with the brokering and trading of energy as atoms combine and break up. These are large and fluffy objects, largely consisting of a large cloud of electrons, very light electrons, and the energies involved in these reactions is very, very, very small. Starting in the early part of the 20th century, we began to find out what was on the inside of the matter, which kept the electrons in close in bound state, which is a cone-like object called the atomic nucleus. It is something which is exceedingly dense. It's made up of protons and neutrons, basically the same particle, one charged, one not charged, and it is a 10 millionth of a billionth of a meter large, or small. The density is extraordinary. Lee has spelled it out there, 1 trillion kilograms per cubic centimeter. A teaspoon would be 100 billion metric tons. Or put differently, if our sun at the end of its life were to become a neutron star, this gigantic star, which has got about 700,000 kilometer radius, would all collapse down. All the nuclear matter would become like one large atomic nucleus. The size of the San Francisco Bay, it would used to be about 10 kilometers in radius. It would be exceedingly small and exceedingly dense. It's something that you and I have no basic intuition about. Lee will use, when he begins to talk about nuclear reactions and so forth, the species will be denoted by the chemical element. They're generically denoted as X. It might be argon, AR. It might be hydrogen, H. It might be bromine, Br. You probably saw the graph that showed up on the web page having to do with the 150th anniversary. It had berkelium 247, except they had Br rather than BK. That quickly caused an uproar. It was taken down from the web page. So shame on Berkeley there. The lower left-hand corner subscript is the atomic number. number of protons in the nucleus, number of neutrons is in the lower right, normally accurate, and the C6, like that. Okay. Protons and neutrons, color-coded. And I think I just mentioned all these things here. Okay. The force associated with nucleons interacting with one another is quite extraordinary. There it is. You see 10 to the 29 times stronger than the strength of gravity. But the force is very small, which is only approximately the range of the atomic nuclei. Atomic nuclei are passing by one another at a distance greater than that. In fact, there will be no interaction. You'll feel the Coulombic interaction, the electrostatic repulsion, very gentle force. But once they get inside there, the probability of there being a fusion reaction in very close analog with the behavior of real liquid drops. Let me show you a movie that I think you'll find a little bit entertaining. Here's an experiment that was done by acoustically levitating a little drop of water that later on we'll mix some in an atomic nucleus as well. So let's actually play this film. There it is going. There's no sound. Experiments like this have been done on the International Space Station as well. There's the little droplet. You can see a little reflection of the light. And what keeps the drop together is of course, surface tension. Atomic nuclei have surface tension as well. It tends to keep it in a roughly spherical shape. And now we're going to start cranking up the frequency to look at very low frequency vibrations and increasingly higher frequency vibrations. It's mentioned in the lower left-hand corner, well, in Eunice, some of you who have taken NE 101, NE 290, or my course 201, we have him regularly as a lecturer. He's one of the world's experts on nuclear fission. And in fact, in the process of nuclear fission, this is what happens. The nucleus will begin to stretch and get to the point where, in the case of an atomic nucleus, the electrostatic repulsion will drive the two fragments apart and then releasing the full 200 MeV of energy. And no kidding, atomic nuclei can be excited by means of electron scattering or proton scattering or alpha scattering. One can look at the states of atomic nuclei that are completely analogous to these excitations. I think pretty soon they're going to start truncating with the drop. So here they're going to break down the surface tension, and sure enough, it will start to disassemble. Life crisis here. So here's the picture. If I had the atomic nucleus, if you were able to see close up the atomic nucleus, providing the charge, holding all the electrons in orbit. And it was the size of a marble here. The electron cloud would extend out across the street over to McLaughlin Hall, the College of Engineering Dean's office there. What we will not get into here is the fact that the protons and neutrons themselves are composite objects made of fundamental, what we believe to be today fundamental objects called quarks. The electron, these very light particles which dress the atom, are responsible for all the chemical binding that governs day-to-day life. As far as we can tell right now, it's the point. Okay, so let's back up here. Hopefully not sent anybody to shock yet. So let's go back and talk about some rudimentary ideas about energy. So there's lots of different types of energy. There's what's called kinetic energy, which is energy of motion. There is potential energy, and there's lots of ways of storing energy. Let's see somebody not from the nuclear department tell me some various ways that we can store energy. Who's not from the nuclear engineering? Who like to take a crack at this?
Batteries, chemical energy?
Yes, chemical energy is one. Right, you're on a roll. What other ways are there ways of storing energy? Potential energy.
Give it all the possible.
Yes, exactly. Gravitational potential energy. Water in a dam, when it's let down over the sluice, releases the energy and becomes kinetic energy, and you can turn it to use this. More coming. I think it's very simple examples. A spring, for example. Okay, lots of things are ways of storing energy that we describe as potential energy. There's thermal energy, which is just simply the kinetic energy associated with a very large number or an ensemble of particles where it becomes inconvenient to do the bookkeeping of all of them. It becomes all potential and no kinetic. The swing briefly stops, and then it goes down again, and all the potential energy is released into kinetic energy here. And so, in a system where there's no friction, how high would the travel of a swing go? Well, you would calculate the kinetic energy, 1/2 mv squared here, and you would set that equal to the gravitational constant, the mass, and the height, mgh, and that's the way it tells you what the height would be. From that, you can calculate how high up the travel will go. Okay, yeah, we just talked about. Lee was quite insistent on several times when we met and talked on the phone that I talk about this and in just a bit more detail. Here is an example again of potential of gravitational potential energy trading off into kinetic energy. So here you have a cart, like a roller coaster at the top. At the top, it might be, for example, motionless or have very little energy. And then the difference in height between here and the bottom will represent the potential energy released, which turns into kinetic energy. And then, of course, the cart may continue going up to a second barrier. So let me ask the following question. By the time the cart gets up here, what is the speed of the cart relative to the cart at A? Is it higher or lower or the same? We're not nuclear engineering.
Higher.
Yes, and because?
As we're
Right. Yeah. So you're just looking at the difference between that point and that point. You've released potential energy, and therefore you will, whatever kinetic energy you had at the first stage, you have to add the potential energy, which is now been released, and is now converted into kinetic energy. Now, we wanted to emphasize this plot because when we get into the world of talking about the release of energy from a very heavy atomic nucleus, uranium or plutonium, which have 236 or 240 nucleons after absorption of a neutron, you will then can provoke the nucleus to split apart, releasing incredible amounts of energy. 100 energy per fissioning system, and the barrier for fission might look something like this. You have a nucleus in a particular configuration with a barrier which prevents it from falling apart, but tickling it appropriately, one can get the nucleus to fall apart, and in the case of the nucleus, you have a very, very, very long slide going down. Once the nucleus fissions into two fragments, the energy, which is largely bound up with its Coulombic energy, will force these two fragments apart, releasing massive amounts of kinetic energy and a lot of neutrons and a lot of gamma rays, and that's where the energy in reactors and bombs come from. And so you'll see that one should really look at this thing in a very literal way as when Lee starts talking about simple properties of fission nuclei. So let's get into doing numbers. The key thing here is not really fundamental understanding of science, but basically the ability to do some calculations with a certain amount of facility throughout the course. So in units which we are very familiar with, which are called the standard international units, MKS, we talk about kilograms, we talk about seconds, and we talk about meters there. And so if I look at, for example, a pitched baseball, traveling at about 90 miles an hour, that will get you a good job. The energy of the baseball there is about 120 joules. It's about 0.15 kilograms, so that would be about the seventh of a kilogram, which is about 0.3 pounds. Something like 5 ounces or so. The potential energy of your car at the top of the 6-story parking garage. Now I'm going to use the gravitational constant again, roughly 10 meters per second. 1,000 kilograms for an average car, 25 meters, and that's about 250 kilojoules, or about a quarter of a megajoule. A joule is not something you and I talk about much every day. I think about the only time you hear it is when you're in college, when you're taking a business class or high school. Power drawn by a typical household appliance, an iron. The last time I used an iron is when my mother was packing me off to college, and I don't think it was used in college. Here, 120 volts, 10 amperes, that's 1.2 kilowatts, and which is a joule per second. Okay, so that's how much energy is being expended per unit time, 1.2 kilowatts. When we get into the world of subatomic physics, these units are not going to be terribly convenient. It's very annoying to talk about the weight of a proton being 10 to the minus 27 something, or electron being 10 to the minus 31 something, and all kinds of things which are important fundamental units of energy have terribly, bizarrely small values in FPS units. And therefore, we develop a new language. And if you're an atomic physicist or nuclear physicist, you're going to start speaking language of electron volts, or atomic physicist. Or nuclear physicists, you would normally be talking about any million electron volts. And so the electron volt here, if I take a battery and I put a 1 volt potential between two electric plates like this in a vacuum, and I release an electron, it will gain energy, or any charged object with one fundamental energy, and it will race across, and by the time it hits the other plate, it will have acquired a kinetic energy of 1 electron volt, which means to say, if I take it and pull it back over here, it has a potential energy of 1 electron volt. If I let it go, and it accelerates, and back, it's acquired an electron volt kinetic energy on the other side. So, over the course of the next couple of lectures, Lee is going to kind of indoctrinate you in this new language, which will make your calculations convenient for the things that you need. So a joule is close to 10 to the 19th, which would be 10 million trillion electron volts. Is everybody comfortable with scientific notation? Good. Okay. Or turning it upside down, the electron volt is 1.6 10 to the minus 19 joules. So let me come back to this point I was talking about before, which is this extraordinary mismatch between the chemical reactions that we're familiar with every day and sort of govern our day-to-day lives and nuclear reactions. If I look at, for example, the burning of hydrogen and oxygen, so if one goes into a world of hydrogen-powered cars, a lot of people think that that's a solution to the energy problem. It's not a solution to the energy problem. It may be a way that facilitates the capture of bad stuff that you don't want in the atmosphere, but hydrogen does not exist naturally. You would normally have to break apart water to form hydrogen or something else. And of course, what does it take to break apart water to form hydrogen? Energy. Okay, so all you've done is simply provide a convenient way of carrying for example, 1 kilowatt of power. You can see how much fuel it would take. Let's go into the world of nuclei and look at the fusion of one of the lightest systems we have, which would be the fusion of a tritium nucleus with a deuterium nucleus. Here, these are some of the very lightest elements one has. One ends up with a very stable nucleus, helium-4, plus a neutron, plus the emission of close to 18 million electron volts. So it's about 3 million times greater energy release associated with a nuclear reaction than the chemical reaction. So as Professor Knott was saying, Lee and I both did time at Lawrence Livermore National Lab. It's a wonderful place to have a career. They even hire policy people as well, although they mostly hire scientists and engineers. Here is the world's largest laser. It's called the National Ignition Facility. It was built, it was completed in 2009, cost about $4 billion. It was designed, by a factor of 50, the world's largest laser. It's the size of the Cal Stadium, 192 laser beams, quite an impressive thing. Go to the website. I think you'll really enjoy it. Let me show a little movie here. What happens is the master oscillator run. They take one seed pulse, divide it up into 192 pulses. They make several passes with a multi-pass laser amplifier. The beams now converge on this large aluminum 30-foot diameter chamber called the Death Star. And inside there was a tiny little thing about the size of a pencil eraser called a hole-wong. It's like a little empty fruit juice bag, inside of which there's a little BB-sized pellet of frozen deuterium and tritium. And the idea is to put 1 megajoule out in, roughly to get 20 megajoules out. Let's see if we can watch this. Those little clamshells that open up the last second because this thing is kept at a temperature of 18 Kelvin, and they don't want the thermal radiation from the chamber to sort of evaporate, cause things. One of my graduate students just accepted a job as a
the universe for billions of years has been lit by the fire of
okay, so let's see.
The universe, for billions of years, has been lit by the fire of countless stars. In these stellar cauldrons, hydrogen nuclei are fused together to form helium nuclei, releasing energy that lights the heavens. Can we build the technology to harness this awesome energy on Earth? As we approach our planet, that is exactly what's happening today. Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, it will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. 85 feet tall, the laser target area building is the size of 3 football fields. Inside are 2 parallel laser bays, each containing 96 beam lines. In this animation, which is billions of times slower than real time, we will follow the process for creating a miniature star in the target chamber by riding along with some of the laser beams. The process starts by first energizing the laser amplifiers in the 2 laser beams by dumping electrical energy stored in capacitors into flash lamps. They convert the energy to light that is absorbed by the laser glass in the amplifier. Later, when the laser pulses pass through the glass, they will extract this energy, thereby increasing the laser beam energy. Our journey with the laser beams begins in the master oscillator room, where a very low energy laser pulse is created. This pulse is only 20 billionths of a second long in duration, which is a beam of light about 20 feet long. It's amplified and then split into 48 laser pulses, which are carried over to the 2 laser bays using fiber optic cables. Here, the 48 pulses are amplified in a preamplifier by a factor of about 10 billion. Then they're split into 192 pulses and sent into the main laser system. As we track 8 of these beams through the facility, you can see the path of the beams highlighted in red. The first amplification occurs in the power amplifier. It has 5 glass slabs that were energized by the powerful flash lamps. Then they travel to the main laser cavity that directs the laser light back and forth 4 times through 11 sets of laser amplifier glass in the main amplifier system. This gives the laser beams another boost of energy. During this time, optical components ensure that the beams maintain their required pulse shape, quality, and spatial uniformity. On the final pass through the optical system, the laser light is allowed to exit and travel back through the beam lines and up to the power amplifier once more to pick up even more energy before heading down the long stretch to the switch yard. In total, the energy of the laser beams is increased a quadrillion times as they travel more than 1,500 meters from the master oscillator room to the target chamber. In the switch yard, the parallel bundles of beams are rearranged into a conical configuration. That's so they can be focused into the center of the target chamber and onto the target assembly. The assembly holds the spherical fuel pellet containing hydrogen. Here you see 8 beams split into 2 groups of 4 beams each. One group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet. The beams then converge on a 10-millimeter target assembly called the whole run, generating a path of X-rays. This causes the tiny target sphere to implode and ignite in a controlled, self-sustained fusion reaction. the same process that powers the stars. This will be the start of a new journey that will bring not only discovery and innovation, but a lasting legacy to the future.
Now, a couple of things about this movie. You saw something at the very beginning, just in a flash. You actually saw an aerial photograph of an underground nuclear test. You saw a sort of a cloud of dust and then a huge subsidence of a crater several hundred years across. That's called the subsidence crater. Since 1962, to the degree that we've done testing, the US and the Soviet Union stopped in 1992. We have the lights back on again. We've all, since 1962, we began doing only underground testing by treaty. Typically, these things are put down 2,000 feet or so in the case of the US, it's in the Nevada test site up north of Las Vegas. And this thing goes off, and it forms a huge classified pattern, maybe like 100 feet in diameter. And eventually, this thing collapses, and then the Earth settles down, and then you get this subsidence crater there. So if you've ever flown from here to Phoenix or here to Albuquerque, sometimes you'll fly over there, and you look down and say, my God, the world looks like a golf ball. You see for many, 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 many miles, you see these little little dimples on the Earth. That was the Nevada test site. The reason this thing was built was not to study astrophysics. It was not even to create this resource of energy. We spend billions of dollars for things which really matter, and it was called a stockpile stewardship program. It's a way of actually validating underlying physics of nuclear weapons in the post-testing era. And you're going to hear a lot more about this from Professor Knocker and Professor Bernstein. Okay, now, it sounds like I've been sort of dissing chemical energy. But if I ask you, how much is a megajoule? We're going to, we spent $4 billion to make 20 megajoules per shot. So the question is, how much is a megajoule? There's an analogy I like. That's a megajoule. You had it this morning. if you grabbed a quick breakfast and ran in here, that's a megajoule. And we talked about lifting a car 75 feet up in the air. Well, the amount of energy it takes is only a quarter of a joule. So you might say, why don't human beings burn up? Well, we're actually, this is one of the great wonders about our system for metabolizing energy, that we do it in a very controlled way. But we actually process massive amounts of energy. Over the course of the day, the amount of energy you radiate in heat is equivalent to about 150 watt light bulb. So I can control very, very foods. So here's another interesting factoid. Which has the higher energy density in terms of ergs per cubic centimeter? In fact, when I ask the question, it might lead you to the correct answer. Paradoxically, by about a factor of 2, it's the jelly donut, not the hand grenade. What's special about munitions?
They bring their own oxidizer.
Yes, which allows them to
Just rearrange themselves.
like that. Okay, so instead of getting a deflagration or a slow burn, munitions are explosives are designed to do very rapid activities, which gives them their effect. Now, here's something interesting. My departmental manager boy, as when I was department chair, that used to chastise me and reproach me for my execrable sleep habits. So in a very nasty way, for Christmas, she gave me a Fitbit. So she could monitor my sleep habits. So this thing is patched into her Apple phone now. I get my finger waves every morning. But it's also made me, I'm sort of obsessive character. I've actually gotten into the whole thing of how many steps I walked and calories burned, all this. And predictably, the first day I got it, I said, damn, I'm not making my 10,000 steps. Went out for a long walk, came back and got sick. So anyway, that's just we made the moves slides. Yeah. I've actually gotten into looking at the backs of oatmeal boxes and other things like that about caloric content and so forth. One final thing, and this is an important number for you. And when I was giving these lectures last year, I always, at the end of each lecture, would make up just what I call the toolkit, a one-page crib sheet of numbers. We talk about in the nuclear weapons business, our scale factor, our ruler for the size of the bag is what we call a kiloton. That's an equivalent. That's the explosive power equivalent to 1,000 tons of TNT, which interestingly, just by coincidence, I think those of you who are scientists and engineers, you know what the definition of a calorie is? Somebody's got it in here.
Isn't it enough energy to raise 1 cubic centimeter of water by 1 degree?
Yes, a cubic centimeter of water by definition is a gram. To raise it by 1 degree Celsius, which is 9/5 of Fahrenheit, a degree Fahrenheit, by 1 degree is a calorie. Now, interesting thing when you're reading your cereal box, what we call a calorie in the food business is actually a kilocalorie. It's really 1,000 fundamental calories. Okay. Just by coincidence, believe it or not, a calorie is also the energy content in 1 gram of the TNT, and it comes out within about 1%, something like that. The world's first nuclear test done at Alamogordo, New Mexico, July 16, 1945, called the Trinity test, released, because a plutonium weapon released 22 kilotons, like that. For the physics and engineering types, 4.2, 10 to the 12 joules. So with that, this will be put up on the web, maybe up there already. That's your toolkit for day 1. Don't worry about these things because Lee's going to go into them in a little bit more detail, but it's there for you to refer back to when you need to. And with that, I'm going to turn the rest of the 45 minutes over to Professor Knott, but I'll take questions right now. Great.
Any questions? There's a lot packed in there.
Be more ways than one. Great. I have a meeting. I'd love to sit. I love listening to Michael last year and talking about history of nuclear weapons and so forth. But I have meetings and I have to teach my own class later this afternoon. So thank you. And I'm happy here because Lee is an important person and he travels quite a bit. So I'll be back periodically.
While I'm switching these computers over, there was an announcement sent out on Wednesday afternoon that included a poll for discussion section and office hours times. So a few people have filled that out, but not as many as we'd like. So please fill that out when you get the chance, because we want to schedule these things pretty soon. So it's linked in the B Courses announcement. If you can't find it, let me know. Even if you don't think you're going to attend them, just fill it out anyway, just in case, because you don't want to figure that out later in the semester that the time doesn't work for you. Do you want me to use it?
Yeah, so. Okay, I'm going to do this one.
If you just do 2 things.
Okay, so the subject of my remarks is sort of how do we get to where we are? And this is a chronology of some of the key developments that led to our current understanding of nuclear energy and nuclear weapons. Can I use this? So I want to begin with this reference to this book, which was published in 1972. Thomas Kuhn was a historian of science at MIT. And he raised the fundamental question, what is the process by which progress in science is made? Scientific progress has a cumulative aspect to it. What I studied at my time leads to what you studied in your time. It builds on itself. And this is a wonderful book to read. It's a short book, MIT Press, I think it's in paperback, 1972, The Structure of Scientific Revolutions. And here's what Kuhn said. He said that if you study a subject, let's say physics, you are exposed to a way of thinking about physics, which he called a paradigm. And most graduates of physics programs spend their careers basically at the edges of the paradigm, modifying it slightly, but not making any major impact on the core concepts of the paradigm. He said that rarely is it the case that the theoreticians or experimentalists discover something which isn't explained by the paradigm. And they puzzle over it. And they determine that maybe they made a mistake. Maybe if they just have to adjust some calculations, the paradigm explains their finding. But sometimes, and this is a less frequent account, they publish new things to suggest that the paradigm actually does not explain what they have discovered. This leads to a debate in the community, and it's often the case, according to Kuhn, that established figures in the field critique the work, say this person made a mistake, the reasoning is faulty. They basically are there to defend the existing paradigm. But still less frequently, the discoverer of this anomaly, Kuhn calls it an anomaly, isn't explained by the paradigm, is not explained by the paradigm. And that leads to the creation, and this could be over decades, of an alternative paradigm. Kuhn says that the body of experts in the field later divide up into defenders of then the new paradigm becomes the central idea, so that new students coming out only learn the new paradigm, and then that new paradigm becomes the existing paradigm, and the process gets repeated. So is it clear? It's a transfer of allegiances from one paradigm, one way of thinking about a problem, to another way of thinking about a problem, when the new paradigm incorporates anomalies that the old paradigm did not fully explain. And Kuhn says in that way, the shift in paradigms this continuous shift in paradigms explains the progress of scientific progress. Okay, so now let's go back in time to, let's see, this should be 120 years ago. a French physicist, Henri Becquerel. And by the way, they're a mixture of chemists and physicists, primarily European-based, not US-based. Becquerel determined that uranium emits radiation. The fluorescent property of uranium salts, by placing a piece of uranium salt on top of the photographic plate wrapped in black paper, the plate was exposed in the shape of the uranium set. So this is actually the first explanation of radiation, and that uranium emits radiation in 1896. Now, one nice thing in the scientific community, even at this time, was that people published their work in scientific journals, just like they do today. They're free journals, they're critiqued, and then the scientific community reads the journal, so they have access to that information. So it stimulates new thinking, new research. A prominent experimentalist, J.J. Thomson, a British physicist, considered one of the most prominent experimentalists of his time, discovered a negatively charged electron, a first subatomic particle, with the so-called plum pudding model, where the plums, which are negatively charged, are surrounded by the positively charged pudding. This was a thesis, this was a paradigm of the relationship of the electrons to positively charged particles, later disproved by a different experiment, an experiment by Geiger and Marsden in 1909. These were some of the experimental antecedents to this young man, Albert Einstein. So who was Albert Einstein? He was German-born in Kaiser's Germany, pre-World War II. He was not a particularly good student, didn't do well in math. He had trouble getting into any graduate program and to get a top job. And he became a patents clerk in Switzerland, in Bern, Switzerland, the capital of Switzerland. And while he was evaluating and improving patent applications, which was kind of routine work for him, he spent time in his apartment at night and on weekends addressing the fundamental properties of the universe. It's extraordinary that this could happen. And in 1905, he published 4 papers, Annus Mirabilis, the so-called extraordinary year papers, that he could publish these 4 papers in 1 year. And in the 5th paper, titled, Does the Inertia of a Body Depend on Its Energy Context? He posed the relationship, he posed it actually in this way, which is not as familiar. Mass equals L divided by C squared. L is total energy. Mass of a particle is M. C is the speed of light. And of course, if you just reconfigure the equation, it's E equals mc squared, which is considered the most famous equation ever formulated. Energy equals mass times the square of the speed of light. So we'll understand the relationship between mass and energy. By the way, Einstein considered his work primarily of theoretical interest, and he was later asked if it had any application to energy release, and he said no, which was not correct. 6 years later, Ernest Rutherford, an eminent British experimentalist, actually he was from New Zealand, but worked at a number of universities in Britain and in New Zealand. And he did an experiment that discovered the atomic nucleus. He also was asked later on, does this have any applicability to the release of energy? And he said no. So Einstein and Rutherford, both extraordinarily significant figures in the foundational ideas of nuclear energy, did not see the linkage between practical release of energy and their theoretical work. He had said this in 1933. He said the linkages between his work and release of nuclear energy is moonshine. Not it's fanciful. And actually, there's a linkage here. I will look at this one. Leo Salar was a Hungarian physicist who had fled Nazi Germany and was in England at the time. And he read a newspaper account of Rutherford saying that there was no relationship between his work and release of nuclear energy. And Szilard, crossing the street in London, this is hard to believe anecdote, realized that it's a possibility to create a chain reaction that a particle can hit a uranium isotope and could release new particles and could be self-perpetuating. This is an extraordinarily important and insightful observation by Leo Szilard. So Szilard, who was not in the forefront of the research of either Einstein or Rutherford, saw the applicability of release of nuclear energy and possibly even of a military application of nuclear energy. Now, going back, Cockcroft and Walton, other British scientists, these were students of Rutherford. They experimentally verified Einstein's equation. Protons bombarding lithium gave off energy and reduced the mass predicted by Einstein's equation. And another student of Rutherford's, James Chadwick, again, discovered the neutron. So these scientists in Britain primarily are developing the theoretical building blocks for the understanding of the nucleus, nuclear energy, and not that it's headed toward any applicability, toward any particular application. They're doing fundamental scientific research. But they're publishing their articles, so all the subsequent scientists can read their work and stimulate their own ideas. In France, two prominent chemists, Frederic Joliot-Curie and Irene Curie, probably aimed particles that could change ordinary atoms from one element to another. In Italy, Enrico Fermi demonstrated that nearly every element in the periodic table could be transformed by bombarding with neutrons, including uranium, than this one element. So you see, it's a synergistic effect of the research in Britain, France, and Italy. Fermi was an Italian Jew who fled Europe and came to the United States. He was at Columbia and at Chicago, and was a critical figure in the development of the atomic bomb. Then, quite significantly, German chemists and physicists Otto Hahn and Lisa Meitner, they found a great number of radioactive products, all elements beyond uranium. Meitner was Jewish and was purged from Nazi Germany. She wound up in Scandinavia. Hahn and his colleague Fritz Strassmann later demonstrated that the uranium atom could be split by bombarding it with a neutron. This is critically important. The uranium atom could be split by bombarding it with a neutron, demonstrated nuclear fission. So that explains a core building block for nuclear weapons. There was a big fight later on about who should gain recognition for this research. Meitner was actually shunned aside by Hahn because the Germans could not acknowledge that a Jew had been significant in research. And Hahn, I believe, Hahn or Strassmann was a member of the Nazi Party. So at this stage, all the research was open, all published in Cambridge, England, in Paris, in the Curies, in Rome with Fermi, in Berlin, small research groups, all talking to each other. Now, this research was known to the Americans, but the United States was not terribly active in this field of research. There was a very talented experimental physicist named Ernest Lawrence. He was from South Dakota, got his PhD in physics from Yale, and was attracted to come to Berkeley to build a physics department. Berkeley's physics department was not very distinguished at the time. And his great achievement was he invented the cyclotron, a circular accelerating chamber between poles of electromagnet. This is a particle accelerator for uranium isotope separation, which led to the discovery of Neptunium-238 that decayed to form plutonium-239. Plutonium-239 is fissionable. With alpha particles in them, it keeps self-perpetuating in chain reaction. Lawrence was also interested in building the physics department at Berkeley, and he recruited a somewhat eccentric character, a theoretical physicist named J. Robert Oppenheimer. Oppenheimer had no real great interest in experiments. He had studied chemistry at Harvard and had applied to a number of these famous physicists to study as a doctoral student, including he applied to Rutherford's lab in Britain, and Rutherford turned him down, saying he's not a sufficiently talented experimentalist. So Oppenheimer studied in Germany at Göttingen. Göttingen is a famous citadel of German higher learning. And then when he was coming back to Germany in the 30s, Hitler had become chancellor in 1933. Oppenheimer left in the mid-30s. And Lawrence told him that if he joined him at Berkeley, he'd have a great opportunity to build a theory group in physics at Berkeley, instead of being at Harvard or Yale or Princeton, which had great theory groups already. So big fish in a small pond, small fish in a big pond. He was attracted to come out here to Northern California. We had never spent any time, although his father was a very wealthy importer-exporter in New York. Always an issue among the laureates. Oppenheimer was described later as an autodidactic and a polymath. You know what that means? What's a polymath? Yes.
Good at a lot of different disciplines.
Yes, you can become a master of different disciplines, self-taught. Self-taught. He was a student of foreign languages. He was a student of Buddhist culture. He was a hyper smart fellow. Okay. In 1940, Frisch and Peerless, also British, noted Niels Bohr. Niels Bohr was from Denmark. Bohr had insights that U-235 was a fissile isotope of uranium, and anticipated that bombarding a U-235 nucleus with a neutron would release vast amounts of energy. They wrote a secret memo to the government at the time. You have to remember or recall, if you don't, what's going on in the world at this time. Hitler had become, he was elected, freely elected, Chancellor of Germany in 1933. He then quickly assumed dictatorial powers. Germany was restricted from military buildup by the Versailles Treaty, which was at the end of World War I. Hitler embarked on a slow but incremental expansion of military capability, thinking if he did it incrementally, the British and the French would not resist him, which was correct. The World War I had been a terrible war. 18 million deaths. Trench warfare of the most gruesome kind. But Hitler had blamed the British and the French and the German Jews for the cause of Germany's defeat. And there was an area of Germany called the Rhineland, which was considered to be a demilitarized zone, and Hitler ordered German troops to re-enter the Rhineland, which is a violation of the Versailles Treaty, but the British and the French did not do anything about that. Obviously, while all these war clouds are beginning to develop, Hitler invaded Austria, a neighboring German-speaking country, in 1938, and Austria just did not resist German occupation. So while all the scientific research is going on, these geopolitical war clouds are building in Europe. And then Hitler made another demand, which was the German-speaking part of Czechoslovakia It's called the Sudetenland. And he said, these are German-speaking people, and Germany is an expanding country, and we need room, we need Lebensraum, room to expand. So he wanted control of that section of Czechoslovakia. This was very alarming to the British, whose prime minister was Neville Chamberlain. And the British population did not want war again, but it was pretty remote for them to go and fight over Czechoslovakia and Sudetenland, which they didn't have much knowledge of. So Hitler organized a meeting in Munich, Germany in 1938. This is the famous Munich Conference. How many of you are familiar with the Munich Conference? Most of you know. So there were 4 representatives at the Munich Conference in 1938. There was Hitler, he was the host, Germany. There was Mussolini, his colleague, fascist dictator from Italy. There was Britain. Neville Chamberlain took his very first airplane flight from England to Germany to attend the meeting. And Daladier, he was the French prime minister who was allied with the British. So when the subject of the meeting was the disposition of the Sudetenland in Czechoslovakia. So who was absent from the meeting?
USA.
USA, pretty remote. Roosevelt is in power, and we're still struggling through the Great Depression, yes?
Czechoslovakia.
Yeah, Czechoslovakia. The subject is the future of Czechoslovakia, but the Czechs were not invited to the meeting. It was the Germans, the Italians, the British, and the French. So Hitler told Chamberlain, who was kind of the leader of that side of the table, that this was his final territorial claim in Europe. He had no further aspirations to expand. He had Austria, and then he wanted the Sudetenland in Czechoslovakia. And that was all. And Chamberlain said, well, how can I possibly trust that this will be your final claim? And Hitler said, I'll sign a piece of paper and pledge to you that it's my final claim. So Chamberlain said, okay. And Hitler signed the document. And then when Chamberlain came home, it was a very famous film spot. He came home to London Airport and he waved this piece of paper. Chamberlain said, I bring you peace in our time. Because Hitler has pledged no more territorial acquisition, and we want to avoid war. So this was later called appeasement. And appeasement at the time was not considered a particularly negative term, but it later became known as placating an aggressor who has an infinite appetite. There was a debate in England at the time, and there was an extreme right-wing figure in the British Parliament named Winston Churchill, who was considered a kind of right-wing kook. And Churchill said about Chamberlain, he said, poor Neville, he said, he seeks peace, but he will have war. Because you can't placate an aggressor. Have any of you seen, there have been a series of films that have just come out recently about Churchill? Anybody seen them all? There was The Darkest Hour, so highly recommended. It's interesting, there was an American studying in Oxford at the time, named Caspar Weinberger. Caspar Weinberger became defense secretary under Reagan. And he was in Oxford at the time of the Munich meeting and was deeply influenced by that. He sided with Churchill, while the vast majority of students sided with Chamberlain. So Chamberlain did the right thing, he avoided war. And Weinberger said, no, Churchill's right, there's going to be war anyway. So, in 1940, Germany went back on Hitler's pledge and invaded several countries of Europe. These sort of low countries, Belgium, Netherlands, Luxembourg, and they invaded France, and they defeated the French in a shocking blow to the West, because the French were thought to have the most mighty armed forces in Europe, but the Germans had some very special techniques. The Blitzkrieg, using fighter bombers to attack suddenly, and tank armies to cluster forces and defeat the French. And then the Germans started to bomb England. So, I should have mentioned, in 1939, September 1st, 1939, Hitler invaded Poland. And that was after the Munich meeting of 38. And the British and the French said, that's it. If you invade Poland, that will be, we will declare war against Germany. So the official start of World War II is September 1st, 1939, the German invasion of Poland. The United States was neutral at this time, neutral. It was not involved in the war. And the Germans, the German Luftwaffe, the very potent German Air Force, bombarded England, including London, major population center, obviously. And this was a question of whether England would survive. In this film, The Darkest Hour was German forces had marched to the coast of France, and there were French and British forces. The British had come to the aid of the French. And the British and French forces were surrounded by the Germans at a sea port on the coast called Dunkirk. Many of you have heard of Dunkirk. So in the film, it portrays Churchill being surrounded by his military. Churchill replaced Chamberlain as Prime Minister of England. Chamberlain resigned. He lost support of his party, and Churchill took over. Chamberlain got sick and died shortly thereafter. Churchill was informed of the dire straits of the British Army, 330,000 men, which was his main ground force to defend the British Isles. They were all surrounded by the Germans at Dunkirk. And the military advisors to Churchill said, there's no way to save them, they have to surrender. Because the British didn't have a naval force that was equipped to traverse the English Channel and saved the British and French forces. So Churchill, who had been a Secretary of the Admiralty in the First World War, he had military policy experience. He said that this was unacceptable, the military advice from his generals. And he said, how about if British private citizens who own boats and ships 100 feet long or more would traverse the English Channel and go to Dunkirk and save the troops. It was not something the military had thought of. This was Churchill's idea. And they didn't really know that it would have any resonance with the British public. But Churchill, who was a resounding public speaker, urged the public to come to the aid of their troops. And 800 boats came to the aid, and they evacuated 350,000 men. So it was a miraculous achievement by Churchill, including French troops. Several were killed, about 50,000, I think, were killed. 350,000 were saved. And the Germans continued to bombard British cities. And then, as sometimes happens, Hitler approached a crucial decision and made a double mistake. He had been very confident because he had often told his higher command that he knew best. And he was told that, his military generals told him that the British and the French would resist in Austria. They didn't. They'd resist in Czechoslovakia. They didn't. So he thought he was infallible. So he made the double decision of stopping the aerial bombardment of Britain and of simultaneously invading Russia, the Soviet Union, which was a catastrophic mistake for Hitler. So, at this time there's a war. And Frisch and Pellet, in the meantime, are looking at fissile isotope separation of uranium. This is moving closer to an applicability of a nuclear weapon. They wrote a secret memorandum to the government about this. After all, the government officials are not included on the referee journal articles of physics and chemistry. But they were told that this was hugely significant, had military applicability. And of course, they were also told that, let's go back, that Hahn and Meitner and Strassman also were aware of nuclear fission. So the British scientists were telling the British government that the Germans had the insight to build an atomic bomb. So the whole essence of the movement to build an American bomb came to beat the Germans to the bomb. Germans, not the Japanese. Okay? A lot more to come, and we'll soon hear would be more to committee. Any questions about that? So again, so two parallel streams: the scientific progress, the paradigm shifts, nuclear energy, and there were continental European scientists. At the same time, the geopolitical shifts leading to World War II. Okay. Any comments or questions? Yes.
So a lot of this was due to the fact that there was competition, not necessarily for the scientific endeavor.
Yes, I mean, it was competition among the scientists, but as they began to realize the military applicability of their work, then they realized it had a direct impact on the geopolitical situation. There isn't a grand plan. There isn't a, someone saying, but if you do this and we do that, I'm seeking to demonstrate this kind of serendipity of the world. Okay, well, thank you. And we'll continue with this chronology on Wednesday.